Welcome to the second installment of our introduction to writing with LaTeX. This is the intermediate level that we've come to, and it is the last of two presentations. In the beginning, we're going to start with macros, and we can start with looking into what is a macro. It is more or less the same as a function, but the evaluation of the body is done by replacing all occurrences of the parameters with concrete arguments. And the result of doing so, the result of replacing those parameters of the body with concrete arguments, that is essentially a text string, and the resulting text is that text string is then inserted in the macro call's place. And this means that it can be a bit tricky to reason about nested macros, so which is evaluated first and how do they interact, and it can be even worse to reason about the errors in them. And we are going to create those errors, unfortunately. And this also means that if you are writing your macros at your peak brilliance, then because you need to be because it's more taxing for you to debug something than it is to write it, then if you are creating macros as smart as you can, then you are by definition not clever enough to debug them. So try to hold back a bit when you do that. The next couple of slides cover some macros that I've written, and I've written them because I have observed some patterns in the text that I write. And for the first one, I have observed that, well, this is because the context for this is that I'm writing a book. I'm writing a textbook for a course that I'm teaching on the first semester in object-oriented programming, and a few of the examples that I'm going to show today are from that course book. In this particular case, I want to make it clear that certain words are technical terms and make them stand out in the text so that they're not confused with ordinary English words. So that the reader will know that they have a special purpose and hopefully try to learn what that purpose is. And I want them to stand out, but I also want them to get into the index so that when the reader sees a word stand out, they know that they can look it up in the index. So for this purpose, I have created the IDX for index macro. It takes two parameters, number 1 and number 2. And then we have the macro body in here. So this is, by the way, a command I'm defining. The macro body within these curly braces. When I want to use it, I write like this. IDX, first parameter and second parameter, which means that number 1 maps to trade-off with a lowercase t, and number 2 maps to trade-off with an uppercase t. This will result in this appearance where trade-off lowercase t is written in purple. It will also result in trade-off with uppercase t being put into the index, given that I have an index. So the next one is that I often need to refer to something of a particular code style or not style, but code type. So that could be a file name, it could be a variable, it could be a type, and I want to make that stand out. Again, so that it's clear that it's something that stands out compared to the rest of the text. And these are things that I would often want to have shown in a monospace font, so constant width font, and some sort of highlighting. So I define macros like this. File name takes a single argument, single parameter, and what it does is to take that parameter and format that in a teletype font, so that's a monospace font, and then take all of that and render that in purple. I use it like this. I just say the configuration is pulled from the file, from this file. And what happens then is that this parameter, that is mapped to this argument. So it's going to appear like this. And the interesting thing here is that when I wrote this, I didn't really care about the specific color. I didn't care about the specific formatting. What I cared about was that in the text of my document, I highlighted, I marked up that conf.yaml, that's a file name. Because then I knew that at a later point, I could just go to the definition of this macro and give it a different color or different formatting or whatever I wanted. So I knew that at that point, it was trivial to change that formatting and have that be consistent throughout my entire document. The next one is that I often find that I make lists in my document. That could be a numbered list, it could be a bullet point list, it doesn't really matter. But the thing I make in a slightly different way is that the lists I make, I often have each list item have some sort of a header. And then I add some text that relates to that header. And for that purpose, I came up with these two macros. And the important one is the last one, desk item or description item. It takes a single parameter and creates an item, which is what we in LaTeX used for the items in both the itemized bullet point list and the enumerate numbered lists. And then I say I use the text description macro, which is defined up here, to format this parameter, which is the header. And that means that when I write this in my LaTeX code afterwards, now that I have defined text description item, then I say, okay, Bonobo, that's our header. And then I write something about that. I can also have a header called given, and I write something about that. And what I do here is that I want to refer to this particular header by name. And now that I have split up the definition of description item into two commands, where one of them is responsible for formatting that header, text description, then I can just refer to that. So that is why I use text description here to refer to Bonobo, thereby making sure that however this text description is defined, that style will be applied to both this line and this line. And that is why Bonobo here is rendered exactly the same as Bonobo up here. Usually I end up having a few lines for each bullet point item, and that looks nice, but it also works in single lines. And as I'm writing that book, I want to sprinkle around some inspirational quotes. So that is some text, it is a source or an author, somebody who said that or wrote it or whatever. And for that I define this macro, which is different from the previous macros because this is an environment we're defining. We're defining a new environment, and we call it inspiration. And environments, they are different from commands in the sense that commands is a backslash, command name, and then the parameters, whereas an environment are essentially two of these commands. It is a begin and then environment name, and then it is followed by an end variable name, or environment name, sorry. So here we have a begin center, end center, that is an environment. But when we define a new environment here, yes, it has two parameters. The first of these parameters has a default value of 0.9. But the key part here is that we have this block and we have this block. When we later on write the start of that environment, so the begin inspiration part, then that part is going to be replaced by this block. And the end inspiration command will be replaced by this block. So whatever we have in between that begin inspiration and the end inspiration, that's going to be placed in here essentially. And what we do here is that we define a mini page with margin pass, and that needs a width. And that width is the width of the current paragraph times this factor, so the first parameter. So let's see how I use this. So here we have a quote by Jane Goodall. You cannot get through a single day without having an impact on the world around you. What you do makes a difference, and you have to decide what kind of difference you want to make. So this piece of code is fairly simple to write. I don't need to look up how to write that because I've done it a few times, and it's a begin-end thing. It's called inspiration. There's the author or the person being quoted, and then there's the quote. And it's going to render like this. If I go back a bit here, then there's this rect left command, which for some reason doesn't work in Beamer. Beamer is the framework I use to make this presentation. So if this text was in a report, if this code was in a report, then this dash Jane Goodall would have been right justified. For some reason it doesn't work here, and I haven't looked into how to fix it, but I'm sure there's a way. Anyways, I also usually use these quotes in reports rather than presentations, so it kind of works out. Another thing I do is that I often want to have boxes, and that box has a title. It could be info, it could be sub-conclusion. And again, it's an environment. And it's very similar to the last one, except that the last one was essentially a paragraph. This one is essentially a tabular environment. It has a header. And it allows us to do stuff like this, create a type box called intuition, and then write some text that is an intuition that we build on and hopefully verify. And when we render that or build that document, it is going to look like this. Now the color looks a bit off, and that's because in the definition, if I go back to that, here, I declare that this cell needs to have a color that is some shade of gray. This needs to have a color that is a different shade of gray. And I am not using a white background here. It is slightly tinted. That's something I do. So what I could do is to go in and change those definitions to, instead of being shades of gray, then being functions over the background shade. That would complicate the example though, and that's why I go for the gray here. Yes. On to part number 2. This is, so now we're done with the macros. And part 2, that has to do with TikZ, which is the framework that it's the largest framework for drawing in LaTeX. And first, we want to load the TikZ package. And the next thing we want, and doing so gives us access to this tikzpicture environment. So environment, that was this begin end thing. So now that we have a tikzpicture environment, let's look at what goes into this and this. So here we have some parameters, and here we have the contents. So this is where we draw. Let's start by looking at the parameters. And what we have a few options there. And I'm going to look into 2 of them today. One of them is called remember picture. And that is a parameter we can give it so that we are allowed to reference absolute positions of specific points that are outside of the tikzpicture environment. So there's a special command that came with TikZ that allows us to put in markers, so invisible markers in our LaTeX code so that we can refer to those when we draw. Remember picture allows us to do that. We also have an overlay parameter, that's down here, and it essentially makes LaTeX treat the resulting tikzpicture environment as having 0 size. And the reason why that is interesting or could be attractive is that LaTeX has this whole engine that tries to lay out things in the most optimal way. And sometimes it's sort of working against you. Using this option causes the tikzpicture environment to have 0 size, which means that we essentially bypass that layout system. And that makes it easier for us to place things where we want them, but it means that we have to work a bit more for it. We can have both options with commas in between. I believe there's a few other options that we can use. I have never used anything else though. At least I don't think so. Yeah. So because it's an environment, and the same would be the case for a command, it is placed somewhere in the code. And it will usually be placed after a paragraph or something like that. So imagine that you have a paragraph and then sort of the cursor is just below that, and this is where we put the tikzpicture environment. But when we place things in that environment, we use a coordinate system like this one. And the origo, so this point, that is at the top of that tikzpicture environment, so just below that paragraph. So the paragraph would be sort of in this area up here, which means that in most cases where you want to draw is down here, which has a negative parameter or a negative y component. That feels a bit weird, but at least in the beginning, but you get used to it. What we want to draw first is nodes. And a node is something that we can place at a specific position. It's typically some text. We can have images in there. We can have some math, but it is something. And around that something, we have a shape. That will typically be a rectangle or a circle or a diamond shape. LaTeX has, or TikZ has, a selection of these, and we just say, I want this. We can also define our own, but that's a more complicated matter. I'm not going to cover that. So that material, the node, is placed at, or that material, so the content of the node, so typically the text, is placed at the anchor point of the node's shape. And the inside of a shape can be filled with a color or a pattern, and all of this is drawn according to some style. I've highlighted anchor point and style because I'm going to cover those two things. let's start by looking at the anchor points. Here we have two nodes. We have a square, so that is a version of a rectangle, and we have a circle. And the next thing I'm going to do is to reveal the anchor points here. There's a lot of them, but what essentially happens is that, well, the first one is we have the center point, which is straight in the center of each of these. Then we have the north point, the south point, the east point, and the west point. Those are basically the same for those. We have the northwest, northeast, southeast, and southwest points, which are in the corners of the rectangle and at the 45 degrees points of the circle. And the next important point here is that it's not on the circle and on the rectangle. It is at the outer edge of the shape. So let's take a look at what that means and what we can use these anchor points for. So we can use this for positioning rectangles. So let's put in a coordinate here. So this is an anchor point at the center of the current page. And I can place a rectangle here. And we do that with this command. You need to remember the semicolon, and whatever text you want inside the rectangle, you put in between these brackets. We place it at the anchor point, which is defined here. We say that we want the anchor, the southeastern anchor of this rectangle to be at that point. So that is the southeastern corner that has to be there. Let's try to place another one using the southwestern corner. So southwest here. And you'll probably notice that this line here in the center appears to be wider than the line at the side, than the two lines at the sides. And that is precisely because those our anchor points are at the outside of the line that outlines the shape. Which means that if we look at the line being drawn around this right rectangle, then the westernmost point of the line going up north-south here, that point is the same point as the rightmost point of the north-south going line of the left rectangle. Which means that because they are right next to each other, you observe a line that has twice the width as the line over here. Now, there are ways to get around that, but I won't go into details right now. We can continue to adding these with the northwest anchor point and the northeast anchor point. And we can do the same with circles. And the only reason why I'm covering circles here is because it's not those corner, in quotation marks, anchor points are less usable for positioning for circles. So here I have my anchor point, and I place a circle here. That is the southeastern anchor point of that circle. I can place using the southwestern anchor point, and so on and so forth. Again, this is not particularly usable, but we can, for this purpose, but we can do it, and I'm sure that there are good applications for it. Up at the top here, I'm referring to the current page. And what that means is that every time we create a TikzPicture environment, that is born with one defined node called current page. That node is completely transparent and has exactly the shape of the current page. So I can use that, and of course that has all the anchor points that we've covered so far. I believe all TikZ nodes have that. But that also means that I can refer to the center of that page, and I can place something relative to that. I can refer to the northeastern corner and place something relative to that, so forth. This allows me to do what is essentially absolute positioning, just relative to the page, rather than relative positioning relative to where we are on the page. So essentially the cursor position, which in many cases is preferable, especially on slides. And I've been talking about coordinates. One thing I can do is I can use a construct called a coordinate, a TikZ construct called coordinate, and that represents a coordinate. It allows me to define a coordinate without having a node. So, for instance, that current page, I can refer to the center of that current page. And then that center is, let's say, about here. And then I can do an operation on that. I can shift that minus 12 millimeters. Remember that the coordinate system, y-axis goes up. So minus 12 millimeters is this, takes the center point of the page and moves that down 12 millimeters. And now we create a new name called center that represents that point. That means that I later on can refer to center. In this case, I create two new nodes. One of them is 2 millimeters left of the center point. It is a rectangle anchored to the east called left. Similarly, I have something that is shifted to the right. These are the x-axis, called right. Rectangle, anchor point to the west. So that means that we have something called left more or less here, something called right more or less here. And these shift operations, so the y shift and the x shift, they can also be combined with a comma in between. Generally speaking, in TikZ, every time you see these square brackets, then you can have stuff with commas in between. Now that we have nodes, we also want to deal with paths. We could also call them edges, but everything we can do with edges, we can do with paths, I believe. So TikZ path is tightly related to the notion of a path that we know from graph theory. And it is a sequence of edges where the destination of one edge is the same. The destination position of one edge is the same as the source position of the following edge. So they are essentially a sequence of edges that are chained together and sharing nodes in between. Each of these edges, they can be drawn according to a number of different rule sets. Either we have straight lines, or we have 90 degrees bent lines. These are all horizontal and verticals, or we have curves. And all of these edges in a path are follow the same styling, or are drawn according to the same styling. This styling is different from the rule sets. But let's start by looking at those rule sets. So here we have some TikZ code. And of course, this goes into a tikzpicture environment. We are defining two nodes. One we call A, one we call B. The label in these nodes are n_A in math mode and n_B in math mode. So that is this one for A and this one for B. So that is, and the positioning is done by some shifting. It doesn't really matter. In all of these examples, those shifts don't matter. It's just to make them look nice. Then we draw some edges. We draw one that is blue. We draw one that is red. Let's start by looking at the red one. It goes from the south anchor point of A to the south anchor point of B. So from here to here. We also draw a blue edge. And note that doesn't go from A center to B center, because then it would start here and end here. What it does is that it goes from the A node to the B node. So Imagine that we draw a line from the center of A to the center of B, and then we intersect that with the two shapes. It doesn't matter if these are circles or rectangles or diamonds, intersection points with the two shapes. So we have one intersection point here and one here, and then it draws a line between those two. Angled edges. Again, we have a point A and we have a point B. Point A and point B. And then we draw two edges, one red, one blue. We draw them between A and B in both cases, but we have different line operators or whatever we want to call them here. Here we have the sequence of a dash followed by a bar. Dash means that we start by having a horizontal line, then we have the bar, which is a vertical line. So first horizontal, then vertical. The blue one is the opposite. First vertical, then horizontal. So first vertical, then horizontal. So it sort of makes sense from a human perspective. The last one is the curved edges. Again, we have 2 points, A and B. Point A, point B. And we are making some curves from A to B. 1, 2, 3, 4, 5 of these edges that are curved from A to B. And when we do that, we need an outgoing direction and we need an incoming direction. The outgoing direction is centered around 90 degrees. That is AO. The incoming direction is centered around 180 degrees. AI for incoming. So down here we have these 5 edges. And I've tried to format it in a way that makes sense. We have the outgoing edge, the outgoing angle, that is the AO angle, plus minus in steps of 10. So we go from minus 10 degrees to plus 20, from minus 20 degrees to plus 20 degrees. So essentially from 70 to 110 degrees. And on the input side, or incoming side, we take as a starting point the incoming angle, and then we take steps of 5. So that is from minus 10 to 10, or from, that must be 170 to 190 degrees. And then I also adjust the looseness, so that is how far this edge goes out and how tight it bends. Now, while this looks fancy, it's rarely something I do in diagrams, at least not in this way. You're going to see in a later slide or two that it can be used to make some nice curves. Those styles I talked about, each node and each path is drawn according to a sequence of style rules. And it's a sequence, it's not a set. Or it's probably a set at the end of the day, but choose to look at it as a sequence. That makes everything easier. Later rules override earlier rules. So we can have conflicting rules in the sequence, but the later rules will override the earlier ones. We can define shorthands for sequences of rules, and we may refer to such shorthands inside of our sequence of rules. This is an example of me defining a style. Style has a name, DEdge or DEdge or directed edge. It has a sequence of rules. It's drawn with a thick pencil. It has an arrowhead at the destination. That arrowhead has this stealth style, that is a type of arrowhead, and it's drawn in black. But let's take a look at what kind of rules are available to us. First of all, we can refer to a previously defined rules. So we can essentially create a tree structure of rules. You could call this inheritance. And again, you can use this to define a starting point and then overwrite that later on in that sequence of rule sets. We can define an anchor point. We've seen that, how to do that. So in this case, we say that I want an anchor point that is at the northwest of our node. Then we have something about how, the visuals of how a node or a line is drawn. We have a line thickness. So think about this as the shape of the node and the shape of the line being drawn with a pen. That pen has a color, that's the stroke color, and it has a thickness. Thin, thick, very thick. I think there's also something called ultra thick, and there's also some thin variants of this. And just like we have named text sizes, we have named line thicknesses. These, the steps in between each of these is significant enough for you to notice that as a reader, but not a whole lot more. So the steps actually makes a lot of sense. There's also a way for you to put in that you want this specific size, but then you're starting to hard code things and you're making things hard. You're probably making things harder for yourself. The shape can also be filled. And if you have text, then you can tell it that you want this text color. I think fill color is usually transparent, stroke color is usually or defaults to black, and text color defaults to black as well, I think. Then you can say that now that I have a node that has some width, should the text inside of that be aligned to the left, the center, or the right? If you have multiple lines, then you need this. Otherwise, it won't break the line. Or maybe it gives you an error. I don't remember. But that's really annoying. You can tell it that you want this node to have a minimum width of this much. Or a minimum height of this much. Or both. And I believe that there's also maximum width and height rules. And you can define this in terms of centimeters, millimeters, inches, pks, ms, points. There's a few more. They don't have meters. That's something you will realize if you accidentally write a single m. And that's probably for the better. You probably want to see that error. And I think this is the last one that I'm covering. There's a lot more, but I've chosen a small subset, or small-ish subset. And the thing is, if you are drawing a rectangle with some text in it, and you don't have a padding between the text and the rectangle, then it's going to look like it's one shape. So by default, there is a bit of a padding in there. And I don't remember how much it is, but it's something like a millimeter or 3, something like that. Which also means that unless you override that default, for instance, by setting intercept to 0 points, you're not going to be able to create particularly small circles. So if you want to create a small circle, you need to adjust this intercept. So what I usually do in that case is that I set that to 0 points, and I set my minimum width and height to whatever I want, and then I get exactly that. We can use derived styles, and that was the first rule that we just saw. So here I define an edge as something that is thick and is drawn in black. I have a directed edge that takes all the rules from edge and builds on those rules. So it's essentially, you essentially take those rules that are up here, copy paste them in there, and continue adding rules. And create an arrowhead at the destination, and we make sure that this type of arrowhead. So here I have 3 points, doesn't really matter where they're placed. We have so 3 nodes, A, B, and C, A, B, and C. And I create an edge from A to B. Edge, that's this one up here, that's not directed. No direction here. Then we have a directed edge from B to C, and we have the arrowhead. We can also use multiple styles. So here we have a point that is a circle. The circle is drawn with a purple outline and it's thick. Then we have HL for highlight that fills it with a bit of purple. So this is 5% purple. And then it draws it with a very thick line. And this I can use for both my nodes and for my edges. I then have a grid of 6 nodes, and I have some edges. Some of these points, or some of these nodes are both points and highlights. And because highlight comes after point, then this very thick will override this thick. So this way I can essentially highlight the path from node A over node E to node C. And you can, and if you squint your eyes, you can see that the line around the circle here of those nodes that are highlighted is slightly wider than the circles that are not highlighted. And the same for the edges here and here. We can also do some more fancy stuff. And as I've been going through my own TikZ education or development, I have discovered certain libraries that I've been loading. And these libraries offer various different functionalities, and the set of libraries I load, that is basically ever expanding. Here are some of those that I load, and that list continues. I'm not going into the details of which can be used for what, but I am going to list a few things that we can do with some of these. For instance, I can align things in what is called a matrix. And this looks a lot like a tabular environment. We have some rows. So this is one row at a time. Each row is terminated by a double backslash. So here we have one row that ends. Here we have another. And here we have the last one. 3 rows. And in each row we have some ampersand separated nodes. These nodes can have names. And if we wanted to give them some text, they would go into these brackets. And then we instruct TikZ to lay out these things in such a way that we have at least 3 millimeters in between each column and at least 9 millimeters in between each row. The whole matrix gets a name, so that means that that is a node. I can refer to the center point of that node. I can refer to the northwestern anchor point of that node. And the whole thing is placed here. Each of these nodes also have points, so I can draw edges in between these two, those if I want to. Another thing I can do is that I can interpolate. So if I have 2 points, A and B, those are called N1 and N2. So this point and this point, and I keep calling them points, but they're really nodes. So this node and this node, and I want to place something right in the middle of those. I could call that N1.5. That would be our node C here. And we have the N1.5 here. That is the label of the node. The positioning is here, and those dollar signs indicate that this is, in the mind of TikZ, a mathematical expression. So we take the position of A, we take the position of B, and we find the halfway point. So we could have put in any number here. We could have put in 0.25, that would be a quarter-way point. We could have put in a negative number, we could have put in a number larger than 1. It is an interpolation between those two, and we can actually across those poles. And the last thing we can do is we can do projections. So here we have 3 points, A, B, and C, A, B, and C. And this point here, I want to find. That will be called point P, and I want to create a line from B to P. So essentially, I want to project B into AC. And so the key to this is to find P. Now P is defined here, and again we have this these dollar signs that is our instruction for TikZ to do something special. And this notation with a triple quote or double exclamation mark with a note or with 3 notes separated by exclamation marks, that is our way of telling TikZ to project B into the line between A and C. And that gives us this position, P. It also allows us to draw a line from B to P, from B to P. So now we have the interpolation, we have the projection. There's a few more of these, and we can combine them to produce more complex scenarios. And that was the end of me introducing material as such, or techniques. The rest of this presentation, or most of the rest at least, I will try to come up with examples of how I've used these things in the past. And I've had trouble coming up with a good name for it, so it has just been called automation, this part. The first, so I have a number of examples here. The first one is a way that I've been producing heat maps. And a heat map is a form of visualization whereby we have a grid and the cells of that grid are colored in a certain way so that we get a gradient, so that we can map an XY coordinate to a color. And we're going to look at a specific application that is very simple, but perhaps not that good of a fit for this technique. But let's say that we are faced with a choice of data structure, and we can either use a list or we can use a dictionary. We'll be doing a lot of insertions and want to know how fast these operations are so that we can figure out which one of these data structures we should use and how we'll. And let's be clear that this is probably not a way to go around that. A lot of this we can figure out by looking up in the textbook, but it could be, we could have similar situations where it makes a lot more sense. So let's take a look at some Python code. So let's go back one here. Should we use a list or should we use a dictionary, aka a map? Python code here, and we have 2 algorithms. You don't have to understand the details of this code, but we have 2 algorithms. I call them algorithms, but yeah, we have 2 algorithms. Either we append to a list or we insert to a dictionary. These 2 algorithms are up here. They each take an n, which is a workload, and essentially perform that operation this many times. So the workload is how many times do we perform that operation. Up here we have a module called time, and if you look up the GitHub repository of this video, you will find all the code that goes into these slides, and you will specifically find this Python file and the Python file behind that time module, I believe. Either that or it's a standard module. I don't remember. But we have this list of algorithms. We have these 2 implementations of those algorithms. And then we have a double for loop. First, we iterate through these two algorithms. Then we iterate through some numbers that we use to calculate a workload. So basically, this is 4 million, this is 8 million, 12 million, and so on. Given that we have the workload and the algorithm, we look up the function of that algorithm using this data structure. So that is either this function or this function. Then we take a timestamp, run that function with the current workload, take another timestamp, and report that, the difference in time. And the report function up here that basically creates a comma-separated lines of these. When I run this on my machine, I get this file with the algorithm, the workload, and the time. Then I can throw that file through this Python program, which I am not going to cover in the same level of detail because it is a bit more complicated and not that interesting. Load some modules, load the input into a data structure, iterate through all elements of that data structure in order to build up a list of algorithms, a list of workloads, and the minimum and maximum cell value. So those are the minimum and maximum times. Then I use that minimum and maximum to create a mapper function that basically scales a timestamp to a value between 0 and 100. So any of the timestamps in that file will now be this mapper function will scale any of the timestamps in our file to a value between 0 and 100. Next, we produce some lines. Those lines go into a file. The lines we produce, that is a tabular environment in LaTeX. And the interesting part of this is, let's see, here, where we create a cell and we scale the background color between red and green according to the output value of this value mapper. So that was a number between 0 and 1, depending on the time. Low time is a 0, high time is a 1. Or maybe it's the other way around. Doesn't really matter. So this creates a LaTeX file that we can include in our document, and it will look like this. So here we can see that a low time, that gives us a pure green value, and a high time gives us a pure red value. And then there's a gradient in between here. We can also see that the largest workload does not give the highest time. That is the second largest workload, and that probably means that something else has been running on my computer. So I should probably have been doing some repetitions here. But that's a separate matter. This is just to show you that we can fairly easily run some code, get some results from that code, produce a data file from that, pull that data file into a different program that presents those data in a way, in a heat mappy way that we can include in our main document. And the takeaways from this is that everything, both of these files, so the code and the processing script, they were run automatically by my build system. I did not have to change anything for those to be executed. So the moment I build this presentation, it first executed the code, then it executed the processing script. I didn't have to do anything manually there. And the output of that was the PDF file. So the performance numbers will always be true to the latest version of that code. And the presentation of those numbers will always be true to the latest version of the processing script. And these two qualities we observe at zero cost to me. I don't need to rerun anything. If I accidentally update something, I will see the result here. That's not so. I can update things all the way whenever I want, and I don't have to worry about things being up to date. This is not necessarily what I want to do, because it's running the code on my build machine, and I might be doing other things on that machine. So there might be reasons not to do this, but that's in part why we have the data collection and the data processing in different scripts. So I could have some system that does the data collection, stores that in a file that is then pushed to a Git repo, from which my build system pulls and then processes the results. This is all fairly simple to implement. The next part is exercise difficulty. As I mentioned, I'm writing this course book, and each chapter is, at the end of each chapter, we have a number of exercises. And I would like to present this to the readers in such a way that I grade each of the exercises, I score them on how difficult they are. And I have two different scores for that. One is how difficult they are in terms of the material of that chapter. And then I have a different score for how difficult they are in terms of other aspects. I'm currently calling that a creativity score, but I'm not really happy with that name. So each exercise is associated with two scores. And I could hard-code this in the document, but that would be hard to manage, especially as my impression of how difficult that exercise is, that changes over time. And it will also be hard to keep consistent because I'm manually adding text here and there and that kind of stuff. So instead, I have a slightly different solution whereby I introduce a directory structure. So folders if you are GUI minded. And at the top level, we have the chapter. Beneath that, we have two things. First, we have a machine readable index file, and I'm using YAML, it could be JSON, that essentially tells us the order of the other files in that directory. So the other files underneath the chapter level. And these other files are directories, one for each exercise. So that index file essentially tells us the order of the exercises. Underneath each exercise, we have a question tag file, we have an answer tag file, and we have a meta YAML file. And that meta file contains the difficulties. The question text contains the description of the exercise. Answer.tag contains a reference solution to that exercise. The next thing is that I have a script that essentially traverses that file system, reads in these different files, the data structure, the file system structure per chapter, and then produces a LaTeX file for each chapter that can be included in my main document. And now that we do know TikZ and we have everything available to our script, we might as well make it a little pretty. So it ends up looking a bit like this. This is an exercise, this is another exercise. Over here we have bars for how hard it is in terms of the topic and in terms of creativity. And the idea here is that I'm also going to make a feedback link that appears over here so that the student can go and click on that and rate the exercises according to these two parameters and maybe even give a comment to the exercise. And by doing so, this is an online system, by doing so, I collect essentially collect the real experiences of students, how they see this exercise, how hard they experience that to be. And if I collect enough of these, then instead of having a bar here for how hard the exercise is in terms of the topic of the chapter, I can have a histogram or some other, it could be a KDE plot, something that illustrates, visualizes the distribution of observed difficulties. And that would be nice. That would give the students a much better, much more clear perception of how other students have seen or experienced this exercise. Now that we are in this document, I could try to shift to it. So here I have the course book, and I can try to scroll down a bit in it. I have table of contents, I have introduction, I have some figures here, and these are all, everything here I think is TikZ code. More or less auto-generated. So here we have a graph, we have some labels on the edges. That's also something we can do. I haven't covered that today. We have some highlights here of a path. We have some tree structures. We have of a file system. Let's see what else. Other kinds of plots. We have an illustration of how a processor works. This is a RISC-V processor. There's a lot of layout stuff here to make sure the things look pretty and are aligned. What else? We get to some more figures here. Also TikZ code. We have there. This is an environment that I made specifically for doing railroad diagrams because I wasn't particularly happy with what else I found. And that is for syntax. I have my exercises here. And what do we have anything more? Oh, there's a color cube because I used colors as an example. I have a bit of math here. And I think that's more or less it. At the end, I have my, oh yeah, one more thing. So let's see here. There's some text. I've highlighted that this is sort of a technical term. That means that virtual machine should exist in the index. So I go down here and we have virtual machine, and there are a number of references to that. I've made sure that places where we have definitions, so terminal are in bold. So terminal is defined there. We have here we have a register file that is defined on page 38, but also mentioned on page 39. Enough of that. So go back to here. Half a year ago or so, we hosted the TikZ conference, and I had a few different roles. One of them was to produce name tags. We had a spreadsheet with 200 plus registrations, so 200 plus people were coming for the conference, and we needed a name tag for each of these. So they have registered for a subset of some planned events, and that registration was spread out throughout the course of a work week. So there were some events. Those events were spread out across a work week, and participants had registered for a subset of these. So yeah, let's continue. The information needing to extract that mapping from participant to what they had registered for was spread out across about 60 columns in a spreadsheet. And the mapping was not clean. So a lot of conditioning would have to be done in order to pull out these things. We also had to have a reference to the full conference program on the name tag, and we needed certain logos for the conference, for sponsors, that kind of stuff. And at the end of the day, I ended up writing a script that loaded in the spreadsheet, crunched the data, and produced one tag file that represents all the name tags that needed to be printed. And that tag file made use of definitions that were made in a different tag file. You can find the source code here, and the result looked like this. But I think I have that over here. So this is the LaTeX file that represents all the pages that had to be printed. This command breaks the page. So that means that here we have one page, and here we have a different page. Those two pages happens to be the same because we wanted our name tags to be able to rotate. There would be a hole about here, and a key hanger would go in there so that the name tag could rotate. And we wanted the same information to be on both the front and the back page. So the document we ended up producing had an even number of pages. So what's going on here? Well, we have the top banner here that states TikZ organizer. It's in purple. That is this part. And then we have the main text in black, the name of the participant, and the affiliation in purple. So that's the name and the affiliation here. Then we have an option banner. That is this part down here. It is only the background color with the rounded corners here. The corners are rounded because the name tag was to be printed on this sort of plasticky cardboardy thing that had rounded corners. And that curvature here was made so that the white border was exactly the same all the way around here. Then we have some static material. So these are the logos of the sponsors, logos of the conference. It was an IEEE conference hosted by SDU. There was this period that gave the participants access to the local tram, and there was this QR code that was put in there. The QR code, by the way, is made by a LaTeX package that was included, and then you write something like QR and give it a parameter that is a URL, and it automatically produces this. Then we have option WS1. WS, that is workshop 1, that is this part. We have workshop 2, that is this part. We have conference 1, 2, and 3. They are here. We have the city tour, the reception, and the gala. And based on what was in the spreadsheet, I essentially put in these lines. So if they signed up for the reception, then I would put in this line. So on and so forth. And all the definitions of these things are in the name tags tag file, somewhere down here. And again, you can see it here, if you care about that. I don't quite have enough to actually run the script there because it depends on certain figures or certain logos and certain logos in a spreadsheet and that I didn't feel comfortable putting on GitHub. The next example is what I call parameterized documents. And this comes from actually this summer. And yeah, that's a lot of text. I'm not going to cover that part by part, but the problem I was facing was that I started teaching the same course on 2 different campuses. So naturally I reused slides, but the slides couldn't be exactly the same. They were mostly the same, but there were subtle differences here and there. So I didn't want to maintain 2 sets of files that were mostly the same, because that's annoying, because you have to, whenever you do a slide update one place, you have to transfer that update to the other document as well. And what I ended up with was a situation where for every little piece of the document that was of the slides, there was a single file. There was a file that acted as the single source of truth. A few different documents went into building each of these slides, but there was no duplicate data. And the solution, well, first of all, normally when you run LaTeX, you run it using a command much like this one. Do a LaTeX -shell escape. This is for minted command inclusion, and then whatever file name I want to convert to a PDF file or build a PDF file from. But if you think about it, then a program like this that takes an input, which is essentially a string, and of LaTeX code, and from that produces a PDF file. Yes, it's natural to pull that string from a file, but it could also be provided by command line, and then it will look like this. So this is a different way of running LaTeX. Instead of taking the code from that file, we take the code from a string that we provide on the command line. And in this case, what we do is that we first define 2 commands, this one and this one, and then we input a LaTeX file, which happens to be this one up here. And this is stolen straight from our build system, by the way. So what happens here is that we define this command. And I'm teaching at 2 campuses, one in the city of Odense, and one in the city of Sonneborg. So these two commands are made in such a way that one of them, here, Odense, that takes the one parameter it gets and essentially just pipes it through. Doesn't do anything with it. And the other command drops whatever it gets. Whatever parameter it gets, it just drops it. Doesn't do anything with it. So because it is the Odense command that retains its parameter and passes that through, then this is the way that I produce the Odense variant of that document. And this, and when I build it like this, then that document and anything that is included from that document will be able to refer to those 2 macros. So whenever I want to place something that only goes into the Odense slides, the slides that are intended for the Odense audience, then I wrap that in this command. Whenever I want to place something that is only intended for the audience in the city of Sonneborg, then I wrap it in that command. And then I essentially run this command to produce for Odense, and I flip the definitions of Odense only and Sonneborg only in order to produce it for Sonneborg. When I run this, I get the result that looks like this. And on the surface, they look pretty much the same. It's the same size, almost the same file name, same title, but the data is slightly different, and the author set is slightly different. Now, there are other differences inside this file. For instance, this is some of those files, or one of those presentations was an introduction of the lectures, and in each of these two campuses, we have 2 lecturers, so obviously that had to be different, but those are minor differences in the grand scale of things. The next one is from a presentation I made a few years back. I was giving a presentation about working with graphs in a distributed setting. And when you do a presentation about a graph, you probably should have some visual representation of a graph. And I needed that. I needed some different properties to be mapped to color and shape. I needed a significant number of nodes and connections, or edges, and that makes the job of layouting the graph non-trivial. And more specifically, manual layouting would have been, well, it would have resulted in pretty bad visuals. So I really didn't want to do that. And then I came across this YAD program, which is quite good at layouting and can work with XML files. Specifically, it can output XML files and does that in a format that is called, let's see, GraphML here. So it is essentially a drag and drop program. You can drag in shapes, you can connect the shapes with edges, you can change the properties, should have some text, should it have how wide and high should it be. There's also the shape, and you have similar properties for the edges. So up here on the layout, you have a number of layout algorithms that takes a lot of parameters. So it does a pretty good job of layouting this graph. I can also, and you should also note that I have used a few different node shapes and node colors. I've done that so that I can match on these, and I can do conditionals on top of these. So we have 3 different colors and 2 or 3 different shapes, something like that. When I save this file, it looks a bit like this, or at least for each node, it looks like this. I have a node ID. I have an X position and a Y position. I have a fill color. That was the color of the node. I have a shape here. And I think that's more or less it. Oh, there's plenty of other stuff, but this is what I care about. Here, I have an example of an edge. There's an ID, a source node, and a target node. It also has some arrows, and that I could care about, but I don't think I do in this particular case. And what I did was that because it was so nicely formatted, I basically defined some regular expression for matching each of those relevant lines that I have just shown you. And those regular expressions I could use to extract those key values. So I used those regular expressions to parse that GraphML file. And this is, again, obviously so the wrong way to do it. It's an XML file, so it should be parsed and then traverse that, or not traverse, but index that tree structure in order to extract what I needed. But it works. So I was happy. After parsing that file, I found the min and max positions both for the X and the Y axis, and I used these to define scaling functions. Then I essentially made a big string containing TikZ code. And first I added styles so that I could style how the different nodes and edges were rendered. Then I added code for each node, applied scalars to make sure that I can define how large do I want this figure to be. I reused the IDs from GraphML because they were at least consistent and they already existed. I then added code for each edge, and that is how I could represent this. Save that string to a file that I then included. And because I had access to the node shapes and the colors that it didn't actually need, I could do stuff with this. And this is more or less the result I came up with, which is a story. So here we have, to the left we have a graph. And to the right we have how that graph fits into a distributed system. So these nodes are hosted on one computer. These nodes are hosted on a different computer. And these are hosted on a third computer. Which means that the edges in between, they essentially exist through a network connection here. So if I want to match this path on the graph, then on the distributed graph, it looks like this. So we start here, we transition within one machine, then we cross a network, go through a few nodes on the next machine, cross a network, go through some more nodes on a new machine, and then cross a network back to the first machine where we match this node. That is how this particular path translates to the graph that is mapped to a distributed system, a specific distributed system. And that whole sequence was essentially the output of that script I made, so that I can just click through it now. And if I were to figure out that, oh, I need a different node, an extra node here, I could go back to Wired, the GUI for editing the graph, make the change, save the file, and the build system would detect that that file is now newer than the files that depends on it, and regenerate those on demand. Again, I didn't have to do anything but tell it to rebuild the main file. And that is fairly similar to how I've been working with figure narratives. So I realized that I was doing a lot of presentations where I had some fairly complex or relatively complex graphical elements, and I wanted to have a sequence of transitions that displays variants of this whereby I make certain elements appear and disappear, where I change the color or thickness of something, or the arrowhead, or the text of something, the width of something, stuff like that. And this, by the way, was before I started working with TikZ. But I wanted to use a GUI to produce sort of the base figure and then automatically derive these different variants. And I wanted to do this in order to create these sort of narratives where I can illustrate changes into the visuals while I explain what is happening. And the setup I came up with looked like this. I used Inkscape. That was the program I covered in, or one of the programs I covered in the last presentation, to produce an SVG file. Then I created a script that essentially took this SVG file and created different variants. So here, 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 and here. Then those were automatically converted to PDF files that was included in my document, from which I produced my PDF. And here, by the way, you see these curved edges that again made from TikZ. But one base document, one script for creating variants of that, and then automatic conversion to these. And the build system made sure all of this worked for me, so I didn't have to run any of this manually. So, Inkscape, I created this figure. It is a circle and a curve and a line. If I save this to a file and open it, it looks like this. The main part is over here. We have the circle here. We have the curve here. We have the line here. And wrapping all of that, we have a group. The circle has an ID. The curve has an ID. The line has an ID. And the group has an ID. And remember these: path 3, path 4, path 5, layer 1. Now I continue. Path 3, path 4, path 5, and layer 1. From the SVG narrative Python package, I import model. Model I instantiate with this file that I've just edited in Inkscape. I get an M, a model out of that, M. I then have this utility function that whenever I call that, it takes a snapshot of the current version of M and stores that in a new file. And that file has a file name that has a component that is an integer that is incremented each time the function is called. Then we get to the main part of this, script. And that main part is to the right. It has 1, 2, 3, 4, 5, 6 smaller parts. And what we do is that we perform operations on M, and then we store. Again, operation M, store. Operations on M, store. Operations on M, store, again and again. So what do we do? First we hide the circle. Circle is the element with the layer, with the ID layer 1. Then we hide the curve, we hide the line. That, by the way, was everything. We store it, so that's a blank file. Then we show or reveal the circle and store it. So we start by revealing the circle. Then we show the curve, store that. We show the line, store that. So now everything is visible. We now hide the group. And since the group wraps everything, then that hides everything. We store it. So this is blank. Then we can stroke the circle. So that is a stroke operation. So essentially us taking a pen to the shape of the circle and drawing that circle with a specific color. FF8800. So that is something that is very red, a bit green, and not blue. And we show the group because that was just hidden. So that means that we can see everything again, and we store that. So now that we have those files, then we need a way of including these that lowers the bar for what it takes to maintain this. So I wrote this macro, include SVG, takes one parameter. That one parameter goes here. So that is the file to include without the prefix and without the extension. When I want to use that, I write something like this. Include SVG vector 5. Vector 5, by the way, was this one, I think. The one that is being stored here because of this. So I have that. And then I have a script that essentially crawls through the file inclusion tree of the root LaTeX document to find all references to this macro. And for each of these, it makes sure that we have the PDFs that will be included here. So basically, whenever there's something that states includes SVG vector 5, it goes in, looks for an SVG file, something that is called vector5.svg, converts that to a PDF with the same base name, and then when that is done, it runs LaTeX, and at that point, this command will go well. So, the first of these snapshots of that narrative, that's the circle, then comes the curve, then comes the line. Now and next we hide the whole group. Then we change the stroke color and reveal everything again. And it looks like that. So I've had the need for this for a number of occasions, and because of that, I ended up writing this SVG narrative Python package. You will find it on pip, so the Python package repository, and you will find it on GitHub. Part 4, the next steps. So this is something looking forward, and the first thing is there's something called KaTeX, which allows us to use LaTeX on the web. Sometimes we can do this through Markdown. You can find more info here. The screenshot is from Livebook, which is a notebook system for Elixir and Erlang code, and you can also write some Python in there. But the cells in that can also be Markdown, and this is an example of such a Markdown cell. And you can see some dollar signs here. Anything I write in between these dollar signs, the system will interpret as LaTeX. So here we have a squared plus b squares equals c squares, and that is visualized here. So whenever I ask it to re-render this cell, it will look like this. And you also have a square root here, and that just looks pretty. Something similar is, if you go to Wikipedia, any page that contains some degree of math, that's probably written in a very similar way. It is at the very least LaTeX. Then LaTeX is used for animation engines. So there's this user or creator called 3Blue1Brown who creates some quite amazing videos. He has a homepage here and a YouTube channel here. If you haven't seen that, I suggest that you go watch it. His animations are typically math related, and he's created a Python library called Manim for creating those animations. There are two versions of this, and it's not like one is significantly better than the other, but they have different strengths and weaknesses. And if you want to take it to the next level, which is significantly harder, then you need to start doing proper tech programming. So you need to work with state, you need to work with loops, and you need to work with conditions. So this should have stated conditions. You should also look into having or getting a constructor methodology for writing LaTeX and for dealing with the errors that comes from that when you make mistakes. And you should start to look into defining custom TikZ node types, edge types, and anchor points. And finally, it's important to realize that while LaTeX puts you in a better position while LaTeX helps you to focus on the structure of what you're writing rather than how it's being presented, it doesn't help you in your writing style. So what is good writing? You need to, it will help you structure things, or make it easier to structure things, to focus on structuring things, but what you write in the individual paragraph, how you organize the paragraphs, how they relate to each other and the sections, how to express the key point you want to express as precisely as possible without having any fluff around that. That is not something it helps you with. That is still something you need to look into. And part 5, which is the last part about exercises. I have 3 exercises here. One is to use TikZ to draw an RGB color cube. So that is a cube that has nodes for red, green, blue, black, cyan, magenta, yellow, and white. and the appropriate edges. If you don't know what a color cube is, then Google it and find an image and try to replicate that image. The second exercise is, let's imagine that you're working on some project where you have to deal with objects that have a color property. And for some reason in that project, it's important for you in a report to be able to quickly state whether one object, let's say 01, it has the same degree of red as another object, or an object has less green intensity than another object, or an object has at least as much blue color as another one. Imagine that this is the case, that we want to be able to quickly state that in our text. Then in order to be able to do that, we would like for these symbols that are composites, we would like to be able to write those using macros. And so the exercise here is to define those macros for equal, less than, greater than, equals, and with these colors. And if you don't know how to put something on top of an equal sign, then look into the code of this presentation and basically steal it. The last exercise is automated test reporting. So you can imagine that you're developing some code, you have a test suite, could be unit tests, and you have to document the outcome of running that test suite. So you probably have access to some test suite that you worked with yourself. Pick one, implement a pipeline that as part of the build process of your LaTeX document, you make sure that it runs those tests, pass the results, and produces a table with the outcome of those tests. And that was the last of these exercises. So I think that's it. And so thank you for following, and hopefully you've gotten something out of it.